Yeah, so this afternoon, we want to continue with the non-biological processes which affect herbicide persistence in the soils. So this is what I'm going to present. Okay, so we're going to talk about non-biological processes. So we'll start with the adsorption. Now, ions and molecules are electrically attracted to colloidal surfaces. The colloidal surfaces are soil particles, and the ions and molecules could belong to herbicides. So the herbicide needs to be in an ionized state before it can be attracted to clay particles or organic matter surfaces. The adsorption of herbicide ions and molecules occur on the clay and the organic matter surfaces. Herbicide molecules left in the solution are available for plant uptake or microbial action. So whatever is left in the solution probably is available to kill weeds, or it can be taken up by microbes. There's also an opposite process known as desorption. It is the movement of the herbicide ions from the clay and organic surface into the solution. Coming, sorry for disturbance. Yeah, I am now having a lecture. Wait for now. Sorry for the disturbance. So desorption is the reverse of adsorption. Adsorption and desorption are in a state of equilibrium. This is the clay particle. We want to look at the behavior of herbicides. So if the herbicide is positively charged, it is going to be attracted by the clay surface, which is a negative charge. And some of the herbicide, which is free, will be available in the solution. So you've got two processes, adsorption and desorption. Desorption is the release of the herbicide into the solution. Adsorption is the attraction of the herbicide to the soil surfaces. Now, if you have got the herbicide which is negatively charged, and you have the clay particle which is negatively charged, there's going to be a repulsion. So you have the movement of herbicide from the clay into the solution. So you have the desorption process. Now, organic matter can also absorb the herbicides and the process is known as the SORPTION, which is actually the partitioning of non-polar herbicide into organic matter. So you can have a non-polar herbicide. The herbicide is not charged. And this can move into the organic matter where you have the herbicide. So H1 could be the concentration of the herbicide in the organic matter, and H2 probably the concentration of the herbicide in the solution. We can work out what is known as KD value, which is equal to the ratio of the herbicide concentration inside the organic matter divided by the herbicide concentration in the solution. This KD value can characterize the nature of the herbicide. There's also KOC, which is this KD divided by the mass of the organic carbon inside this portion, which is absorbing the herbicide through the sorption process. So you may find that in some countries they use KD and KOC values to describe the characteristics of the herbicide. In Zimbabwe, we use a clay if we want to decide on the rates to apply, because our soils do not have enough organic matter. So KD and KOC is not important for us. Now let us look at the ionization properties of the herbicide. If the herbicide has got positive charges, we say it is cationic. And because of the positive charges, it will be attracted to be soil particles or colloids and tightly bound. We have such herbicides like paraquat and glyphosate, which have no soil activity because they are tightly bound to the colloids. These herbicides are very sensitive to the quality of water which is used for spraying. Loss of herbicide efficacy can occur due to the use of dirty water. So loss of herbicide efficacy can occur when these herbicides come into contact with the soil. So the soil can reduce the effectiveness of the herbicides, especially for post-emergence herbicides. This is paraquat. It has 2 positive charges, and we say it is cationic. Now we have got soil particles or soil colloids. We have this paraquat, which is cationic. It is tightly attracted to the soil colloid. This is the reason why if you put paraquat into the soil, it can lose its activity. And as for glyphosate, glyphosate is negatively charged. What can happen is that the soil colloid, which is negatively charged, attract calcium or ions or ferric ions, Fe++ or Fe with the 3 charges, or aluminium. Now, in this case, we are using calcium, which also occurs in the soil, which is attracted to the soil colloid. So what can happen is that after attracting the calcium to the colloid, there could be extra positive charges around the calcium, which will then attract the glyphosate. This is how glyphosate, with its negative charge, is attracted to the soil corrode with also a negative charge, but via the calcium bond. We want to examine the effect of soil pH on the soil, on the atrazine efficacy. Most of our soils could have a low soil pH of around 4.3. Now, these soils make herbicides inactive. What can happen is that if we take atrazine, for example, and spray it at a soil with the low soil pH around 4.3, hydrogen ions will move to the 2 nitrogen positions in the atrazine ring. Remember, atrazine it has a benzene ring. This process, we call it protonation. And this protonation occurs under very low pH, for example, 4.3. Now, when atrazine is taken these hydrogen ions, it becomes positively charged atrazine. Now, when it is positively charged, it is now attracted by the negative soil surfaces or soil particles, and it is now strongly bound to those particles. This can cause atrazine to lose its herbicidal activity, and this is a common problem in this country, in Zimbabwe. The rate of breakdown of atrazine is also very fast at a low soil pH. So remember, if we are having a low soil pH, the herbicides like atrazine may fail to kill weeds. Here it's an example of atrazine at higher soil pH 7. This is Cholocho communal area where atrazine can be very efficient in killing weeds. In Chota communal area with a pH of less than 4, atrazine may fail to kill weeds. Now let us look at the effect of soil pH on atrazine efficacy. Now, pH of 5 makes atrazine less protonated. In other words, it's not going to attract the hydrogen ions. So atrazine will become available in the soil solution. So increasing soil pH will increase atrazine efficacy. So here we have got a diagram of a soil particle showing soil pH of 4.3. And we have got a positively charged atrazine, which is attracted to these soil particles. So at low soil pH, atrazine is tightly bound to soil particles, and it may not become available for killing weeds. Now, at higher soil pH, let's say greater than 5, the soil particle will not attract atrazine. So atrazine will remain free in the solution, and it is ready to kill weeds. Here I'm just going to show you the interpretation of soil analysis with regards to pH. Soil with below 4.5 pH is very acid. The one between 4.5 and 5 is strongly acid. The one above 5 is satisfactory for production of most crops. So it is this pH 5 above 5 and this one which is around 5 where atrazine may work, but below 4.5 atrazine may lose its efficacy. Here are just examples of soils which were collected from communal areas with their respective soil pH. Here you can tell where atrazine is going to work. For example, in water, it can be problematic to use atrazine. But in some of these areas, I think atrazine can work very well. So if the soil is acidic, we can reduce this problem by liming of soils or adding cattle manure. Cattle manure can override soil pH effects because it tends to raise soil pH. Now, there are certain weak forces which can attract neutral molecules of herbicides. So a weak attractive force among it's non-polar herbicides. The molecule will have a zero charge if it is non-polar. So soil pH does not influence neutrally charged herbicides. For example, trifluralin. This is trifluralin with a zero charge. So this one is not influenced by soil pH. It is attracted to soil surfaces by what are known as van der Waals forces. So this kind of herbicide may not be influenced by changes in soil pH. Soil moisture, those are talking of what can happen to the herbicide when it is applied to the soil. We said it can be attracted by soil particles, or sometimes it can be neutral. It's not attracted by soil particles. Water can play a very important role. So let us focus on soil moisture. Water competes with herbicides for binding sites on the soil particles. This can be important for the herbicide EPTC. If you spray it on dry soil, EPTC tends to bind tightly on the dry soil. Under moisture stress, plants are unable to take the herbicide. So this can happen under wet conditions. Most of the herbicide is in the soil water. there's less on the soil colloid. But if you have dryness, you'll have more of the herbicide clinging to the soil particles, and very little will be available. No wonder why moisture is important for the efficacy of herbicides. Again, the addition of soil moisture activates the herbicide, especially for the pre-emergence herbicides, which are applied directly to the soil. To move into the weed zone, this is what we call activation. So adequate moisture ensures good weed control. So that was for soil adsorption. A lot of things actually were happening in the soil. Now we move to photodecomposition. This is the effect of radiation on the herbicide molecules. It is the molecules with carbon and nitrogen in the ring which can undergo photodecomposition. You have the wavelength of 290 and 450 nanometers. That is where you have excitation of electrons. This can cause the bond rupture. The processes which can alter the chemistry of the herbicide is oxidation, reduction, hydrolysis, substitution, and the isomerization. So photodecomposition is the light which can induce the herbicide breakdown. The herbicide, if it is applied to the soil surface, it can actually react with the soil. So there could be purely chemical reactions which lead to herbicide degradation. There's no living organism which is involved. Soil pH determines the dissociation of herbicide molecules. Again, hydrolysis, oxidation, and reduction can take place without the presence of enzymes from living systems. This is just, a straightforward test tube reaction. We have got triazines, sulfonyl urea herbicides, which can undergo hydrolysis under acidic conditions. So if we spray atrazine at low soil pH, there could be hydrolysis. So these were the 7 processes which we have just gone through. Here I'm just going to talk about some of the experiences of herbicide persistence in Zimbabwe. So there have been some studies which were done. We have got the first study which was done by Chivinge and Mpofu using metallochlor, terbutaelazine, atrazine, and prometon. These were found to be persistent in the soil for 12 months under sandy soils. Zaranyika and Nyandoro showed that the persistence of glyphosate was biphasic under aquatic conditions. What they meant is that at first, glyphosate is a rapid disappearance. Then later on, it is degraded slowly. So there's fast degradation at first, then slow degradation in the last phase. Mushambi in 1993 indicated that the half-life of atrazine was 59 days for ready soils and 24 days for sandy soils. Probably I will have to define what is a half-life. Now, on this graph, we've got time on the x-axis in months, and we've got the herbicide dosage on the y-axis. Now, if we apply 4 liters per hectare of the herbicide, with the time, this rate, this dosage will fall down due to herbicide degradation. It will fall up to a certain level. But the time taken to reduce this rate to half, which is 2, is what is called the half-life of the herbicide. So the time required to reduce the original dose by half is the half-life. It's a property which is used for herbicides when we are talking about how long they stay within the soil. There was a study on the persistence of atrazine under conservation agriculture. In this case, the researchers wanted to find out whether atrazine could persist in conservation agriculture. So these graphs are showing where there was atrazine applied and the controls, and that is the growth of soybean. In most cases, if you see the lines touching together, or if there are no differences, it means the atrazine residues were minimal. In fact, all of these graphs suggest that there was very little atrazine left in the soil after using the atrazine for one season in conservation agriculture. So what are the factors which affect herbicide persistence? First, it's the amount which you use when spraying. If high dosages are used, this can increase persistence. So there may be a need to reduce herbicide doses. So we have to do it using herbicide mixtures, low doses deliberately, or bending. So we can play around with the dosage so that we can control herbicide persistence. Binding affinity. This is now the characteristics of the soils. Herbicides that are strongly attracted to colloids are less available for microbial degradation. Clay soils, you have a long herbicide persistence, whereas sandy soils, you can have short herbicide persistence. This is due to the clay content. So clay can prolong herbicide persistence. Soil temperature and moisture. Atrazine persistence was affected by the seasons. Now, in a dry season, atrazine could last for 9 months. And in a wet season, it could last for 7 months. Also, high temperature tends to increase degradation. Soil amendments can also influence herbicide persistence. For example, addition of organic matter, e.g. cattle manure, this can decrease herbicides in the soil by adsorption. Another aspect is that organic matter may increase microorganism populations, which can decrease herbicide persistence. So I just want to summarize what we have been talking about. I will just use one slide for this, I think. So this is the summary of herbicide persistence. We have got number 1, leaching, number 2, volatilization, number 3, microbial breakdown, number 4, plant uptake or plant herbicide breakdown due to plant uptake. Number 5, adsorption by soil colloids. This is when we also talked about soil pH, soil moisture. Then in number 6, photochemical decomposition. And the last, 7, which is chemical decomposition. So all these processes will account for herbicides which are applied to the soil. Sometimes these processes may explain why herbicides are not being efficacious or effective. They can also account for why herbicides may kill crops during rotations, residual. I'm talking of residual herbicides. So this is it on soil persistence. So that is the end. I'll have to stop sharing. Hello?
Hello, Doc.
Yeah, so that is it on the persistence. We have got 7 processes which you need to worry about. This is the case which applies to soil-applied herbicides. Any questions?
None from me, Doc.
None from me, Doc.
Okay, so what we will do, I don't know, what is your program like tomorrow?
No plans yet.
Yeah, we can have just another hour or less. Then we talk about herbicide registration, and that will be the conclusion of your module.
It's okay.
After that, I will then give you the assignments. I think it will be very appropriate now to give you the assignments there, because they will also trigger your revision.
Okay.
Yeah, they will actually help you to revise.
Okay.
These are, they are like pillars, you know, you just have to hang on to them. So we'll meet tomorrow, same time.
Okay, Doc. Thank you.
Okay,
Doc,
thanks.
enjoy the
You were
rest of your
seeing the
day.
slides properly.
Yes.
Yes.
Okay, yeah, thanks very much.
Right.
Bye.
Okay.
Thank you. Bye.
Okay.